Thank you, John. So, yes, thank you very much. I was so happy to get invited here that I carefully read the title of the workshop and the title of the thematic semester or year in IAS. So the program, the full program is called Geometric Structures on Three Manifold, and this week is about contact structures, foliations, and flows. So if I take all those words and I look at what kind of mathematics I've done, that there's only one topic I could talk about today, right? And so it's a bit old. I mean, the non-trivial things that I will explain were published in 2012. So I apologize if you know part of the story. I guess most of you don't know very well this story, but that's okay. That's what I'm going to talk about. So I assume you've all heard about Bill Thurston and stuff like this. So you know that in three-manifold topology, you've got the three-manifold, which is your topological background, and you put some geometric structure on it, a nice Riemannian metric, and then you get all sorts of wonderful topological consequences on the three-manifold, its fundamental group, whatever. Right. In contact topology, the topological background is M equipped with a contact structure. So this is a contact three-manifold, which is closed. Okay? And this is, for us, this is the topological background. I mean, really, the contact structure has no local invariant. There is a local model for the contact structure. The group of contact transformation acts transitively on k-tuple of points for any k, stuff like that. So this is, for us, this is part of differential topology. And we would like to add, but it has global properties, right? Like tightness, you've heard about already several times. If you need definitions that I don't recall from previous talks, you should tell me. But there are global things happening. And so the question is, does there exist extra geometrical structure on M psi? We could put on M psi to get global consequences out of local constraint. So for instance, having constant curvature -1 for a Riemannian metric is a local constraint, right? And so we want that kind of thing. And there are many kind of geometrical structure you can put on a contact manifold. So maybe that would be, you have the world of contact metric manifold. So those are contact manifold endowed with a Riemannian metric, which is special, and I'll come back to that later. But there are also CR geometry. So people doing strictly pseudo-convex CR geometry. So here the extra structure is a complex structure on the contact plane, and maybe I should put calibrated here, but probably it will be too small to see anyway. So if you also choose a contact form, you get something which is a calibrated CR structure. And you could also go for sub-Riemannian structure. So sub-Riemannian is when you put a scalar product on the contact plane, but not on the full tangent space. But if you have a scalar product on the contact plane, you can still get a distance by looking at the shortest Legendrian curve between 2 points, and this is a topic of sub-Riemannian geometry. And in dimension 3, these are all the same. So all the same in dimension 3. So this is an accident of low dimension. There are not enough dimensions for those fields to separate. But since I'm sticking to dimension 3, they are all the same. And we hope that maybe we can have local constraint on this kind of extra geometric structures, and out of those local constraints get like tightness, symplectic fiability, that kind of things. But first, I'll start with more basic and general things to have a slow start. So I start with the extrinsic geometry of plane fields. So I think this is due to nobody in particular. I mean, many people came out with what I'm going to discuss right now independently. so here psi is, so still I have a 3 manifold, and psi is any plane field, but I will use the same convention as Thomas. I use the vocabulary of contact topology for everybody. So for instance, a curve gamma is Legendrian if it's tangent to psi, so the speed is in psi. And I'll say Legendrian even if the plane field is not a contact structure. And I also use the notion of the characteristic foliation for every plane field. So the characteristic foliation already was mentioned in several talks, but it's simply how if you have a surface inside M, then you get a singular line field, which is simply psi intersected with Ts is a singular line field. So it's singular because it could happen at some point that psi equals Ts. So in that case, you don't get a line, so you get a singularity of your line field. But anyway, it integrates to a singular foliation. So this gives you a singular foliation, which is denoted by psi s, as in Thomas' talk. So these are just notation. So now, what is about this extrinsic geometry? So assume I've got any Riemannian metric on M, and I want to say how I want to explain how psi moves measured by G. First, we learned already in Jonathan's talk that contact structures are about rotating. So how do we see this? So you get a local frame around some point, which looks like this. There is psi at P. I mean psi, and you just take a unit normal vector n, and then x and y are inside your plane field. They are Legendrian plane fields. And what does it mean that psi rotates along Legendrian vector field? It means that if you got phi t, the flow of x, say, and then if you look at what the contact structure does along the flow, you measure the angle, say theta of p and t is the angle between n and phi minus t push forward y. So you flow along x, and you look at the angle between with the normal, and then it's a relation that if you look at the derivative of this angle at t equals 0, then this is something like g of Lie bracket xy with n, and then if you look at alpha, so that the kernel of alpha is psi, so this is a contact form for psi, contact form. This is a one form defining your plane field psi, and you choose the one which has unit norm and define the correct co-orientation. Everything is co-oriented. So you choose a unit one form defining psi, and then you compute alpha wedge d alpha, and this is theta prime times the volume for G. So this function I denote by theta prime of P. Okay, so indeed, the contact condition that alpha wedge d alpha is everywhere positive, say, is indeed something about rotation of the contact of the plane along tangent vectors. Okay, so this is all very elementary, but we already have a way to, when you have a metric, we have a way to measure how fast a contact structure is rotating. So it's not only that it's rotating, you can say how fast. And then there is the second fundamental form. Second fundamental form. So you know the idea, if psi is a foliation, you look at leaves, and leaves are surfaces in your Riemannian 3 manifold, so it has a second fundamental form. But I say that leaves are useless in this discussion. So you can get a fundamental form, a second fundamental form, which will be a quadratic form on psi. So quadratic form. So I guess the way I wrote it is a symmetric bilinear form. Maybe I should, say psi to r, and this is a quadratic form. And how do you do that? Then you choose a point P, and you've got your plane psi P with its unit normal n, and then you choose one more vector so that this is the x you want to compute second fundamental form on, and then you just pull back inside, so this is inside TPM, you have the pullback by the exponential map of psi, so now I'm in a Euclidean space. I consider only a small neighborhood of the origin. And I have the plane spanned by n and x. And I want to look at the characteristic foliation here. So this is the characteristic foliation. And because the contact structure is transverse to this plane, in the neighborhood of P, I see a bunch of curves. And there is one curve going through P. And this curve has a curvature, geodesic curvature. Like you just look at this circle and put 2 of x is plus or minus, depending on orientation, 1 over r. I mean, the same thing you would do in elementary course about surfaces in R3. And this gives you a quadratic form, and it's not hard to check that this is given by the following formula. It is nabla xx scalar product with, so I guess I switched notations, with the unit normal if, yeah. Okay, and this is a quadratic form, so it has a determinant with respect to the metric, and that I denote by ke, so it's the extrinsic curvature of this plane field, and it has half a trace, which is the mean curvature that I denote by h. Okay? And so in this extrinsic geometry of a plane field, for any plane fields, the most remarkable case is when the second fundamental form is 0. So you say that psi is totally geodesic if its second fundamental form vanishes. And of course, if psi is a foliation, it means that the leaves are totally geodesic submanifolds. But again, you don't need leaves. What it means is that if you have a geodesic which starts tangent to the contact structure, then it stays tangent forever. Okay? So it means, yeah, maybe I don't need to write this. So for instance, if you give me any contact structure which exists in nature, say the standard contact structure on S3, or the contact structure which is a canonical one on the space of contact element on the surface, or maybe the Levi-Civita connection of a metric with, say, of a hyperbolic metric, say, Levi-Civita seen as a plane field on the unitangent bundle. All those contact structures, they are totally geodesic for more or less obvious Riemannian metric. Or maybe if I need to write down only one example, if I consider on R3 the kernel of dz plus r squared d theta, which may be the first contact structure you ever saw. Maybe the first time you saw it, you didn't notice, but this is totally geodesic with respect to the Euclidean metric. This is a nice exercise if you've never seen this. Any Euclidean line which is somewhere tangent to this contact structure is everywhere tangent to this contact structure. And of course, this is a restrictive condition, right? You don't expect these will be very common. But there is still a result about them that I proved in 2007 in my thesis. So if you've got a closed Riemannian and psi is a contact structure which is geodesible, which means there is a Riemannian metric such that I don't really care about the Riemannian metric. I mean, if there is a Riemannian metric such that psi is totally geodesic, then psi is universally tight, symplectically fillable, and weakly symplectically fillable. So in a sense, I mean, not in a sense. I mean, this is one result I was looking for. I mean, this condition of vanishing of the second fundamental form is a local condition, and then you get a global result, tightness and more. And if you don't know what universally tight or symplectically fillable means, you just need to know. I mean, it's more than tight. And I mean, and it's a global property. It means interesting from the point of view of contact topology. So when I proved that, this is the very first theorem I proved in my life, so I thought I would never forget any detail of the proof. Okay, but there is something I remember. The thing I remember is that it starts with Riemannian geometry, and the first step is to say that for any plane field, being totally geodesic is the same thing as saying as if you look at the orthogonal line field, this is the orthogonal of Xi, then this defines a one-dimensional foliation which is Riemannian. It means its holonomy preserves a transverse Riemannian metric. So it's if you see, you want to say it's locally a Riemannian submersion, the metric you're looking at. And because of that, there is lots of rigidity coming from two-dimensional Riemannian geometry. And about at the time I was born, in late 81, someone called Yves Carrière completely understood this one-dimensional foliation with transverse Riemannian structure. And so it means that by 81, the Riemannian part of this theorem was done. And then the result of the Riemannian part is that they exist only on Seifert manifold and some T2 bundle. So T2 bundles with hyperbolic monodromy over the circle. And we know what they are. I mean, the plane field on the Seifert manifold is geodesible if and only if it's transverse to some foliation by circle. So some Seifert fibration. And then once you know that, okay, contact structure on T2 bundles were completely understood by work of Giroux and independently Kohonda. And so let's see if Seifert manifolds, which were not completely understood, but with more work, so these Giroux-style techniques. So this was Carrière, and Giroux techniques give the theorem. So what is disappointing is the interaction between Riemannian geometry and contact topology is very little interaction. I mean, there's a Riemannian side, and then contact topology takes over. Yeah.
Particularly, you're thinking about non-compact manifolds?
About non-compact manifolds, I don't really know. Let me see. No, it's false for non-compact manifold. Because I know Thomas tried to tell you otherwise earlier, but it's not true that a contact structure which is transverse to a foliation by line is tight. No, you told us that it was a lie. But, so I remember you, it was a lie. And so there are over-twisted contact structure on R3 that are transverse to every vertical lines. And those are geodesible. Okay. So what else? So now we turn to people doing foliations. Because, so of course, Carrière and Gis were doing foliation, where they were interested in two-dimensional geodesible foliations. But then what else? Then they tell you that this H function is also something nice. So there is a theorem, I guess by Sullivan, but maybe I need to put more names. I need help from foliation people. So that F foliation is taught if and only if there exists a metric such that H equals 0. So leaves are minimal surfaces. Should I put other names? No, Sullivan only. Okay. And so that's pretty encouraging. I mean, maybe this is the right class of contact structure to look at. Of course, it's much weaker than geodesic. But the problem is that in the contact case, this is an empty condition. I mean, in contact, G always exists. And if you know a bit about for instance, the theory of foliation cycles by Sullivan, and I mean the criterion for having interesting stuff it becomes completely void for contact structure because there is this d alpha. I mean the contact condition alpha, which d alpha is positive. It exactly means that d alpha is an exact 2 form which is positive on the kernel of alpha, and then you expect this whole Sullivan thing to collapse completely. And indeed, this becomes an empty condition. But before I explain why it's empty, I need to start following another thread. Maybe what we want is not the extrinsic geometry of the plane field, but the intrinsic geometry. Of course, in the foliation case, you can restrict the Riemannian metric to the foliation, and you get a foliation on Riemannian metric on surfaces, and there you already have some interactions between geometry and topology. So maybe we want intrinsic geometry of Xi. And this is in line with this idea of sub-Riemannian geometry, that we should put only a Riemannian metric on the contact structure. But as I said, in dimension 3, this sort of this collapses with all the other things that are written there. So what happened is this. So assume, so you start with G sub Xi, which is a metric on Xi only. I said there is a canonical way to extend this to a metric on the scalar product on the full tangent bundle. And this is something which does not exist in the foliation case. So the point is that because everything is oriented, you get an area form on Xi, given by G Xi, plus orientation. And then, starting from there, there is a unique alpha, one form, so that the kernel of alpha is Xi, and again with co-orientation, and d alpha restricted, yeah, I mean if everything is oriented consistently, d alpha restricted to Xi is the area form that we had previously. So you see, because d alpha is symplectic on Xi, and of course if you multiply a given one form by a positive function, then when you restrict to Xi, the positive function, the derivative does not appear. So you can just adjust to any area form you want. And this is the proof of this observation. And then I'm doing something wrong because I got yeah. Okay, then you have every contact form comes with a Reeb vector field. So you have R sub alpha Reeb field of alpha. So this was defined before. So again, the definition is this is a vector field whose flow preserves Xi and such that alpha on R alpha is 1. So flow of R alpha pushes Xi on Xi, and alpha of R alpha equals 1. Maybe it's not the definition that was given previously, but it's equivalent. And you can just extend. So then you have the projection of Tm on Xi parallel to R alpha, and then you define G Xi hat to be G Xi after projection plus alpha square. So it means that R alpha is now perpendicular to Xi and has norm 1. Okay, there's another way of reading this formula. And together with the knowledge of G Xi, it determines G Xi hat. And this is a very nice class of metric. It has one drawback from the perspective of Riemannian geometry. This class of metric is not invariant under homothéty. If I have such a metric and I multiply it by positive lambda constant, then it won't be of this form anymore, which is a bit bad from the perspective of Riemannian geometry. So the definition is a metric G is compatible with Xi if there exists a metric on Xi, so a sub-Riemannian metric, and a positive constant, such that G is lambda times the extension of G Xi. So, I mean, there are other, the way I tell this story, it seems it's only imposing invariance under homothéty, but there are also other good reasons to do that, but not today. So I've got a class of metric, and I claim that this class of metric in particular proves that the idea of mimicking geometrical tautness, asking that H is 0, was a bad idea, or at least not sufficient. So there is a proposition, but I don't know who proved that, but probably Chern. I don't know. I mean, ancient. So first, G is compatible with Xi if and only if, first, the rotation speed is constant. So remember this rotation speed that I introduced earlier. And I have something stronger than alpha wedge G alpha is theta prime times volume. Actually, the Hodge dual of D alpha is theta prime times alpha. Okay? But then that's a condition in tensor. And this implies a couple of, so this is a characterization, and then you have properties. You have properties like H is 0 always, and what else I want to say? The Reeb vector field is geodesic. So it's if you follow Reeb orbits, those are geodesics of your Riemannian metric. And maybe I want to say something more. I think I had 3 properties. No, I think that's okay. That's enough. So for instance, if you look at S3 with round metric and standard contact structure, so if you don't know what is standard contact structure on S3, you know what is the Hopf fibration. So you have this action of S1 on S3. So you've got a foliation by circle, and those circles are geodesics. And the standard contact structure is the orthogonal complement of those circles, of the tangent space to those circles. So in particular, in this example, so maybe the H equals 0 is not so clear, but at least the geodesic property is clear. Okay, the Hopf circles are Reeb orbits that are geodesics in S3. But they exist, those metrics, so it seems like a very strong restriction on a Riemannian metric. I mean, you don't expect a random Riemannian metric to have a vector field with geodesic orbit. And, but they exist on any manifold, because contact structure exists on any manifold. You can just pick any scalar product on Xi and then run this extension procedure, and you get a metric with this property. Of course, this somehow prevents the geodesic flow of the manifold to be very interesting. Right? And for instance, this is incompatible with having a hyperbolic manifold. I mean, there are very strong results due to Ghani-Zegib saying that if you have a closed hyperbolic manifold, there is nothing like a totally geodesic vector field, even in low regularity and stuff. So that won't be a hyperbolic metric. So we need to remember that when we need open questions later. Not really, no. It could be, I mean, T3 also has an example with a flat metric. So flat T3 is also an example with a standard contact structure. But then this forces positive curvature somehow. And but we already have, maybe we need some proof. No, there's been too many definitions. So there is already one observation about the spatial geometry of those metrics. So assume you have a contact manifold and G is any metric such that the unit normal to Xi is
geodesic. So in particular, G could be compatible with Xi. Okay? So e.g., okay if G is compatible with Xi, but it's a bit more general. Then we already have something to say about contact topology. You know, usually when you want to check whether a contact manifold is tight or over-twisted, if you want to prove it's tight, you have to hunt over-twisted disk a lot. I mean, it's not easy to prove that there is no over-twisted disk, because over-twisted disk could be hidden. But not in this situation if you look at a ball. So if you have any radius r which is less than the injectivity radius of the metric, say at some point P, then there are two possibilities. Either the ball around P with radius r is tight, so there is no over-twisted disk at all in this ball, or there is some radius r0, so that for all radius between r0 and r0 and capital R, not only the ball is over-twisted, but the sphere is over-twisted. So the sphere around P with radius r contains an over-twisted disk. So over-twisted disk, remember, means the following picture. So over-twisted disk, it means we have a disk, and there is the characteristic foliation has one singular point in the middle, and the boundary is a regular closed leaf. I mean, there are several definitions, but the definition that I want to use is this one. And the characteristic foliations look like this. So all leaves start from the singular point in the middle and they spiral towards the boundary. And this, I claim, this picture will be on every sphere up to a certain, starting from a certain radius, if the contact manifold is not tight on this ball. And this is clearly the weird point of this talk. So if there is anything you should disbelieve, that this is this proposition. But I will prove it anyway. But this is really weird. Okay? From a contact topology perspective, it doesn't make sense. I mean, over-twisted this should be nastier than this. I mean, they should hide somewhere. And I don't really know if there are examples when this appears. Then maybe over-twisted disks never live in a ball below the injectivity radius of the manifold. Maybe. And it's hard to tell because contact structure you find in nature are tight, and those are the only ones where you have hope to have a Riemannian metric that you understand well enough to compute balls and stuff. I don't know. So what's the proof of this proposition? Well, the first observation is that for any radius, the characteristic foliation on the sphere has only two singular points. I mean, that's exactly two singular points. So what is that? You look at a sphere and assume there is a singular point. So singular point in the characteristic foliation means the contact structure is tangent. So this is not P, this is Q. So P is in the middle, and you have a point Q with a singularity. And this means that psi Q is the tangent space to the sphere at Q. This is the definition of singular point. Okay, but now we know that the unit normal to psi at that point, you know what it must be, because we have a Gauss lemma telling you what is the unit normal to a sphere in a Riemannian manifold. We know that Gauss lemma, it's a bit Gauss lemma read backwards, but it's still it's still Gauss lemma. You know that if you follow the geodesic from P to Q, this gamma is the geodesic from P to Q, and the tangent space to S at Q is the orthogonal of the speed of this geodesic. Okay, so we learned that in this situation, this is also gamma dot of, say, R, and gamma dot R is equal to N. But n is totally geodesic by assumption. So it means that this geodesic gamma is actually an orbit of n. Okay? So gamma is an orbit of n. And it means that I know where I was here. This was also n. And this was the contact structure at P. And this is one possibility for a singular point. And the other possibility is on the other side. And those are my two singular points. And that's all. Okay? So that's the proof of the first claim. Is it okay for this part? Only two singular points? And then we learned from Eliashberg, and especially that spheres with only two singular points, they are somewhat important. I mean, they are the key players in the proof of the classification of over-twisted contact structures. And at least the traditional proof. No, there is a modern proof that has not much to do with it. But so we have this. And now what happens in a movie of characteristic foliation? Now I'm looking at psi, with the foliation printed by psi on spheres of growing radius. And in the beginning, the dynamics I see is simply north-south dynamics. All leaves go from first singular point to another one. I guess I should put my arrows in the other direction. Anyway, so this is north and south. And then maybe nothing happens. So maybe this stays like this forever. And I claim that in this case, you can reconstruct completely the contact structure from the movie of foliation. This is also something which should be shocking for foliation people. But in contact geometry, it's true. And in the movie of characteristic foliation, on the sweeping by surfaces, you reconstruct psi. So in that case, psi is tight on the ball because it's standard, and then you have Benker telling you it's tight. If some closed leaf appear, then of course on this sphere I see, so the typical picture would be something like this. So if the closed leaf appear, it's degenerate at first, it's attracting on one side and repulsive on the other side. And on this sphere, of course, I see an over-twisted disk. But my claim is this will never disappear. And this will never disappear. Maybe there will be more closed leaf appearing, some of them disappearing. But the claim is that if one closed leaf ever appeared, it will stay forever. And so the precise claim is the leaf closest, say, to North Pole never dies. And why is this true? When you have to remember that contact structure rotate, and they always rotate in the same direction. So assume you've got this situation. So which one I want to? Yeah, probably this one. Say assume the North Pole, so I've oriented everything, and the North Pole is repelling, and assume I've got a closed leaf going west. Then I say this closed leaf can never die. And it will also prove that the same argument proves that the first leaf to appear has to go west. So what happens when the radius increases from that point? And the contact structure is rotating like this. So the new characteristic foliation will enter the polar region like this because of rotation. And then the North Pole is repelling, and you have this foliation entering. And then Poincaré-Bendixson tells you there is and there is no other singularity, remember. So Poincaré-Bendixson gives you another closed leaf in this region. See? And that's the end of the proposition. So I should have maybe explicitly attributed, this is part of the work with John and Rafford. And so this is the first remark where we see over-twisted disks in those kind of Riemannian manifold under an assumption which is slightly weaker than compatibility. But of course, this proof is not robust, right? If you change geodesic to quasi-geodesic, like we learned this morning, we should do that. Then the proof completely collapses. Okay, but maybe something still remains if you have only information like quasi-geodesic. And the reason why quasi-geodesic is still interesting is the work of Hofer in 93, I think. Sorry. If you have a closed three-manifold with a contact structure, if there exists a Reeb field, so it means a vector field which is transverse to the contact structure and whose flow preserves the contact structure, and there are lots of them. If you have a Reeb field without contractible closed orbit, then psi is tight. So I'm already late, so I won't say much about this, but the proof is well known by now. You assume you have an over-twisted disk, and you can run some holomorphic curves, and the holomorphic curves will find a contractible closed orbit. But I want to read the theorem this way. If there is a Reeb field without contractible closed orbit, then psi is tight. So in particular, if M is hyperbolic, and there is a Reeb vector field which is quasi-geodesic, then psi is tight. Psi is universally tight. So we have very few ideas about how contact topology could interact with hyperbolic geometry, and this is basically, I think, the only one. So this really one of the important goals of my talks is to tell people in this room who know about quasi-geodesic vector field that we care if you can build, if you have an understanding of when a hyperbolic manifold has a contact structure with a quasi-geodesic Reeb vector field, that would be great. So where are they? There's one here and another one there. And you should, I think this is an interesting question. And no. This follows from Hofer's result, because if you have a quasi-geodesic, then its leaf to the universal cover is a quasi-geodesic. In particular, it's not closed, and if you have a contractible orbit, then it leads to a closed orbit in the universal cover. No, so yeah, then this part is a theorem. So this is a corollary of Hofer's theorem. I mean, the problem is find examples where you can apply this. I mean, it's pretty. I mean, probably if you have a hyperbolic manifold which is fibered over the circle, and then Thomas told us about those contact structures which are homotopic to the foliation by fibers, and then probably that there is a quasi-geodesic Reeb vector field in this case. I don't think anyone ever checked even that case. I don't know. So now I need to tell you about, maybe I don't have time. I had a nice transition to the next topic, but I think I'll skip the transition because I'm late. And so let's pretend there would, maybe I tell about the nice transition. So if you want but I don't write it, okay? If you want a uncheckable criterion for quasi-geodesicity, you just ask that the Reeb vector field has an acceleration which is not too big compared to the curvature of the metric. So if you ask that the nabla R and R as norm 1 in norm is less than -1 if this is a hyperbolic metric with curvature -1, then of course you won't ever be able to check this. But then you get something which is quasi-geodesic, but you can also directly see that in the universal cover there won't be any closed leaf, closed orbit. The reason is if you look at balls in the universal cover, their curvature, the curvature of their boundary, will never get smaller than 1. Okay, in Euclidean space, if you look at a very large sphere, it becomes almost flat. But in hyperbolic space, things don't work like this, and so it will stay convex. Keep a certain amount of convexity. So say 1 if really have a hyperbolic metric. And then if you have this geodesic vector field, if it has a closed orbit, it must be tangent to one of those spheres. And at that point, it has an interior tangency, and the acceleration is too small to be inside a ball with such curvature. And this is the transition to the convexity discussion. So convexity. So in Riemannian geometry, there is a whole zoo of convexity notion. But in my case, say I've got a domain inside MG with smooth boundary. And I say this is J convex if, I wanted one line for this. Okay. If any, let's do it like this. If any geodesic tangent to the boundary is locally outside D, so the picture is like this. You've got your domain D, and you've got a geodesic here, and this geodesic so it touches D at this point, but it's outside the domain. So it's the same thing as saying that the second fundamental form of the domain is positive with correct orientation. And now the magic is I can change color and define J convexity. So now I've got a domain X inside a complex manifold or almost complex manifold with smooth boundary is J convex if any holomorphic curve, J holomorphic curve, tangent to the boundary of X is locally outside X. Okay, and of course the picture is the same. So, so if you don't know about J holomorphic curve, you'd simply think that Wj is Cn, and a holomorphic curve is a holomorphic map from C, say from the unit disk in C. This is a local thing, from the unit disk in C to Cn. Okay, and you ask that if it's tangent to the boundary of the domain, it stays locally outside. Exact same definition. And then you can hope to play with this. So the relevance of the last bit. So to the first definition, we already saw in the quick transition that if you control this kind of convexity in Riemannian geometry, you can prevent existence of closed geodesic. So maybe there is this definition of the convexity radius of G is the supremum of the set of R such that all balls with radius R are J convex. And here you should think this is roughly half the injectivity radius. So for instance, on Sn with radius 1, with a curvature 1, you know the injectivity radius is pi. You can go almost to the other pole, and the convexity radius is pi over 2. So until you reach the equator, if you look at grid circles, they are locally outside the polar region, say. But if you go beyond the equator, you'll get in this situation where say this is P, and there you have a grid circle which is locally inside the ball around P. And so this is at least part of the relevance of this radius in Riemannian geometry. And in a complex geometry, if you want to run anything like the proof of Hofer's theorem inside a ball or inside a domain, anything which has boundary, you don't want holomorphic curves to hit the boundary of your domain. If you have convexity for the boundary of the domain, it will prevent escaping holomorphic curve. Because if you've got a family of holomorphic curves which tries to escape this domain, at some point it will have an interior tangency with the boundary of your domain. So this gives you this result. And I claim that combining those ideas and compatible metrics, then you can get estimates on tight balls. So given G, which is compatible with Xi, you get almost complex structure on the product R times M, which is the kind of almost complex structure that people use in symplectic topology. And with the following proposition, or lemma, that we also proved in this paper, is that if D is G convex, then D times R is J convex. So this is something which was well known in the case where J is a Keller complex structure on R times M, but in the general case, you have to do a computation. You see, I mean, convexity has to do with second derivative, and so there is some kind of second derivative which controls convexity on this side, so it's a second fundamental form, and there is something which is called the Levy side on this Levy form on this side, which is also about second derivative, and there is a relation between those which prove this proposition. And then you get, as a corollary of this proposition, so you should say that proposition plus Hofer implies that if the radius, some radius is below the convexity radius of a compatible metric, then the ball with this radius is tight. Okay? Because the convexity prevents holomorphic curves from escaping, so you can run holomorphic curves in this ball times R, and it gives you a contractible Reeb orbit, but this contractible Reeb orbit is a closed geodesic too, because the Reeb vector field is geodesic, but a ball below the convexity radius cannot contain a closed geodesic, because the reason I've explained earlier. It would be tangent somewhere to a sphere which is convex, tangent from the interior. And so this is a version of quantitative Darboux estimates. Of course, we know from the first lesson in contact geometry that any point in a contact manifold has a neighborhood which is a Darboux ball, so it's embedded inside a standard R3, so it's tight. But the size of this ball is not controlled. In this situation, we have control on the size, because this convexity radius can be estimated using Jacobi field or stuff like this. So easy comparison theorem in Riemannian geometry. So I say easy comparison theorem because this is also a transition to using hard comparison theorem in Riemannian geometry. I mean, comparison theorems in Riemannian geometry, they don't stop with Jacobi field. I mean, you have all this thing by Berger and Klingenberg and stuff about estimating the injectivity radius using subtle methods and starting with Toponogov comparison theorem for triangles. And so using this ingredient, so I don't remember, I have no numbers in the proposition. I mean, using the weird proposition about geodesic spheres containing over-twisted disk plus this corollary that I just have here, plus classical but non-trivial classical hard Riemannian geometry. So classical here means late 50s, early 60s. So Berger, Klingenberg. Maybe I should start with our Toponogov. Berger, Klingenberg. We can prove the following result. This is probably the only really non-trivial result by us that in this talk. So the theorem is that if M3 has a compatible G which is complete and positive curvature, which is not a surprising assumption, has compatible metrics tends to have positive curvature, which is 4/9 pinched. So this means that if you look at sectional curvature of any plane field, the minimum number that you find is at least 4 divided by 9 times the maximal number. So for instance, if the sectional curvature is constant, that's good. But then you're allowed to have non-constant sectional curvature up to this 4/9 ratio. So this means K mean is bigger than 4/9 K max. Then universal cover of M equipped with the lifted contact structure is isomorphic to S3 with tight contact structure. So how does the proof work? So first, the fact that the universal cover is S3 is not surprising. It was known before, so it looks like the classical sphere theorem by Berger and Klingenberg, except that you expect 1/4 here. But since 61, we knew that the universal cover would be S3. The content of the result is that the contact structure is standard. Okay? So what is the proof? So you start with this pinching, and those people doing Riemannian geometry tells you that you can cover the manifold with two balls. A big ball, but still below the injectivity radius, and a small ball which is convex in this Riemannian sense. And now we know that because of classification of contact structure on S3, we only need to prove that psi tilde is tight, because there is a unique tight contact structure on S3, that's Eliashberg. So we already had, so we use heavy machinery here on the Riemannian side, also on the contact topology side with Eliashberg. And now assume there is an over-twisted disk somewhere. It may be intersecting both balls. But if the big ball is over-twisted, no, so first the small ball, using Hofer and this comparison of convexity, the small ball is tight. So the small ball is tight, then using again classification result, a small ball is standard. And in particular, there is a contact vector field pushing everything towards the boundary, everything except a point. You can remove a point from the ball and push everything by contact isotropy towards the boundary. So if there is an over-twisted disk somewhere, the small ball pushes it off to the big ball. And then the big ball fights back, because the big ball is over-twisted. And because of the weird proposition, the over-twisted disk has to be seen near the boundary of the big ball. But the boundary of the big ball is inside the small ball, and you get a contradiction. Okay, and that's the proof. And I don't have time to write it, because I want to discuss whether or not this is optimal. I mean, it's already, it's the only, if you remove my thesis where the interaction between Riemannian geometry and contact topology was non-existent, right? The Riemannian side was done when I got born, and then I did the contact topology later. Then this is the only result where you have intricate interaction between Riemannian geometry and contact topology. So in a sense, we could be happy and not ask for optimality, but let's move on and ask, is it optimal? And first I should mention that it has been improved. So it's not optimal because Yang Jie and Yang Wang, not long after, improved the pinching to 1/4. And so their proof contains ours. So they took all our ideas and they added one more idea. And using this extra idea, they were able to improve to 1/4 pinching. So now it looks like the classical statement of the sphere theorem. But in dimension 3, the classical statement, the sphere theorem is not optimal in dimension 3. It is optimal in even dimension. So in dimension 3, the best known result is, remember, Hamilton. Hamilton in 82, the first triumph of the Ricci flow, long before Perelman, said that if you have Ricci positive, implies S3, and universal cover is S3. Okay, so that's much stronger than quarter pinched. And so maybe you ask, maybe the optimal result is this. If you have a compatible metric and Ricci is positive, then universal cover is S3 with standard contact structure. But this would be very unlikely. You see that the problem is that the reason why we used sectional curvature, Riemann sectional curvature of the Levi-Civita connection is because we had those guys to help us. And also, so there is Riemannian geometry is well developed, comparison geometry. And also in the proof of the weird proposition, we had this Gauss lemma. And Gauss lemma, maybe you don't know, you don't notice this, but this uses that the Levi-Civita connection is torsion-free. So if you have a metric connection which is not torsion-free, then you won't get this lemma. So we really need that. But if you stop thinking about the proof and just figure out, we had to impose this homothétie invariance in the definition. It's not longer there. So the Levi-Civita connection is not very natural with respect to the contact geometry because it's too isotropic. I mean, it doesn't really see the difference between the contact direction and the other directions. So there is a more natural connection from the point of view of contact geometry, which is Tanaka-Webster connection. And I don't have time to define it, or at least state the characterization, but this is a connection which is metric and has torsion. So it's not the Levi-Civita connection, but it also preserves Xi. So Xi is automatically totally geodesic for this connection. And it preserves Xi, and it preserves lots of other things. So this is a connection which has which cares about the contact structure. Of course, the definition of compatible metric also cares about the contact structure. But once you have the definition of compatible metric, you use the Levi-Civita connection, which doesn't care. And then this connection has a curvature. And then the scalar curvature of this connection is called the Webster curvature. And it's something very important in CR geometry. And because I told you that all this CR geometry, contact metric, sub-Riemannian, and dimension 3, they are all the same. Of course, there are formulas relating Webster curvature to other things. So in our case, this is secretly the extrinsic curvature of Xi plus the sectional curvature of Xi plus 3/4 times theta prime square. So in particular, if Xi were a foliation, you would get the sectional curvature of the leaves, the intrinsic geometry of the leaves. And the 3/4, which is here, if you recognize it from the O'Neill formula, it's the same 3/4 as in O'Neill's formula. Anyway, so there is this, and there is also the norm of the torsion, so measuring torsion. And again, I could tell you what it is. This is square root of minus extrinsic curvature from the point of view of Levi-Civita connection. And what I say, and I'm almost done, is if you want a wild conjecture about what is the optimal sphere theorem in contact geometry, you need the following observation by Agrachev and Barilari. And if you don't know who is Agrachev, it really means that we contact topologists should listen to people doing sub-Riemannian geometry. If you do sub-Riemannian geometry, you know who is Agrachev. But we have this problem that contact topology is somehow in isolation from people doing CR geometry or sub-Riemannian geometry. I think we should change that. And what do they observe is that among contact structure and Riemannian metric, which are left invariant on a Lie group, so you take your list of three-dimensional Lie groups and you look for left invariant contact structure, then SU2, of course, all those functions W and norm of tau, they become constant if everything is left invariant on a Lie group. So they are left invariant functions. So SU2 is characterized by the inequality. W, so which one is this? Yeah, W is positive and less than norm of tau, something like this. So you've got this, I mean, some inequality, and it's equivalent to having some operator which is positive definite, but anyway, like something which looks like Ricci curvature, Ricci operator curvature seen as an endomorphism is positive, and so the wild conjecture is, maybe this is the optimal statement of the sphere theorem. Maybe if you've got any m psi g with 0 less than w less than norm tau, that again you can rewrite in other terms if you want. This implies that psi is standard. I mean that m tilde psi tilde is standard S3. So the reason why this is a wild conjecture is because the only evidence is the above proposition. This, of course, is very weak evidence. But at least this is something you could try to disprove. And at least this would be optimal for sure. Because, for instance, T3, the 3 torus with Euclidean metric and standard contact structure with any torsion, any one of the contact structure Thomas was telling you about, they are the boundary case. They have W equals norm of tau. And I have no idea how, I mean, I have the same idea you have. Maybe we should find a Ricci flow to do the job for us. But it doesn't really count as an idea. So you should work harder. And I'm done.